All right. So if you remember, I had mentioned sound earlier, even when we started based on a string, and had said how sound is a longitudinal wave, and what that basically means is when sound propagates in some direction, the particles are moving to and fro about their mean position along that same direction. Okay, so if, for instance, if I have a tuning fork over here, okay, and the tuning fork के कारण the surrounding air molecules, they start vibrating and they start propagating sound in this direction. Okay, they start propagating sound in this direction. Of course, all the particles don't keep moving, okay, like a train. They what they do is they have their mean positions and they oscillate about their mean positions. Okay? So you find that your particles in general oscillate about their own mean positions, and that's how sound propagates. But they don't oscillate in this direction. They oscillate in the direction of your propagation. So what's going to happen? Imagine these are 5 evenly spaced molecules. As the prong of the tuning fork goes out, okay, as that goes out, this prong is vibrating. So let's say this moves outwards. As that happens, this molecule is pushed closer to the first molecule is pushed closer to the second molecule. Okay, so now the first and the second molecule are quite close, and they don't like that proximity. They start repelling each other. Okay, they're closer than they want to be. So they're antisocial. They start repelling each other. So you can see them push each other apart. Okay, so they're going to try and push each other apart. So in the subsequent motion, what's going to happen? This guy is going to go back to its mean position. This guy is going to now go to its extreme position, right wala extreme position. Okay, so as the prong retracts, goes back to its natural length. This guy has come back to its natural length, but this particle has moved to its extreme position. Having moved there, these two are now closer than they wanted to be. Okay, so what will happen now? These two will, try and repel each other. So they'll push each other apart. So as they push each other apart, what's going to happen? This guy is going to come back to its mean position in the next instant. This is going to move to its extreme position. This guy reaches its mean position with some momentum, so it will continue moving. So in the next instant, what you're going to see is the prong has retracted. This particle is over here, the first particle. Second is back at its mean position. The third is now at its positive extreme, and the third is now very close to the fourth. And they don't like that. So the third and fourth are going to repel each other. But the third mean पे वापस पहुंचेगा और fourth mean से displace हो जाएगा. ठीक है? Fifth के पास जाएगा. So in the next instant that we observe, you're going to see this particle now having gone back to its mean position. But now this particle, the second particle which crossed its mean position earlier, is now at its negative extreme. So now these two particles are very close to each other. Okay. So now these two particles are very close to each other and they're going to push apart. These two particles, the fourth and the fifth particle, fourth extreme position पे गया, the fourth and fifth are very close to each other. उनके बीच में you can observe that right now at the moment, this particle के आसपास कोई भी नहीं है. This particle is feeling very lonely. So what I want to demonstrate through this is, of course, it's just a crude drawing, but what I want to demonstrate through this is, you can, of course, understand how sound starts to propagate. This particle goes to its extreme position, and then that phase of going to the extreme position gets transmitted down the chain, like a domino effect. So, इसके है ना ये extreme position जाने के बाद second particle extreme पे गया, third particle extreme पे गया, fourth particle extreme पे गया. So accordingly, that disturbance is passed down the chain. ये particle वापस mean पे लौटना भी keeps getting passed down the chain. ये particle negative extreme पे गया, uska bhi motion keeps getting passed down the chain. Okay, as we go ahead and ahead in time, as we draw more and more instances, you will see how a particle ka motion keeps getting transferred to the neighboring particles. And with some time delay, they also start oscillating the way the first particle was oscillating. So that's how a wave is propagating. Okay, the displacement of this particle is getting transferred to the neighboring particles. That's one way of seeing how sound propagates. Another way of seeing how sound propagates is as a compression pulse. What is a compression pulse? A region of, I've defined it on the next page, is just a region of higher pressure higher than normal. Okay, like when the molecules are equally spaced, the pressure was, let's say, the atmospheric pressure. But now in this instant, wherever I've highlighted the diagram in blue, you can see there the molecules are very close to each other, closer than what they normally would have preferred. So this was a compression pulse created over here. And you can see how that compression pulse also has been transferred down the chain. Okay, the compression pulse has been transferred down the chain as time elapsed. Following the compression pulse is a rarefaction pulse. This is a region of low pressure in comparison to the normal pressure, because this time where the rarefaction pulse is, uske aspas the molecules are further than they should have been. This is a low density region and thereby a low pressure region. Okay, so this rarefaction pulse also was more or less created over here when that particle was at its second particle was at its extreme and this guy was at the mean. And then you can see how this also started getting propagated down the chain. So when we say sound propagates in some direction, there are actually two things that are in a way propagating. One is the way the first particle oscillates, that uska displacement, right? That particle going to its extreme position. So that displacement, that phase gets propagated down the chain as we wait with time. Subsequent particles will go to their extreme position. एक वो होता है, and उसके साथ साथ simultaneously this region of high pressure followed by a region of low pressure, that keeps getting propagated down the chain. So eventually you'll have, as sound propagates, you'll find a train of compression and rarefaction. You find a region of compression, a region of rarefaction, a region of compression, a region of rarefaction, and as a train that keeps moving in the forward direction. Okay, so this is just a little bit of visualization to just, it's okay if you don't draw this. I mean, there's no point in drawing this, but yeah, it's just a little bit of visualization to help you understand how sound may simultaneously dono ho raha hai. Displacement kind of disturbance is getting propagated, and also a compression and rarefaction disturbance is getting propagated. And one notable difference from wave on a string is the fact that this disturbance was along the line of propagation. The particle oscillates, every particle, if you look carefully, they're oscillating to and fro, but they're oscillating to and fro along the line of propagation. Yeah? This guy has gone to its extreme. It will then later come to its mean, then it will go to the negative extreme. All these oscillations are happening along the line of propagation, like a domino effect. Okay. Any doubts in this page? Let me know if you want me to wait. I'm connecting this with the next page for a theory likha hai. Okay, nobody is saying wait. So 5, 4, 3, 2, 1. Okay. Yeah. So compression pulse, just defining it as a region of excess pressure above the atmospheric pressure Okay, so that was what I labeled as blue in the previous graph, a region of excess pressure above the atmospheric pressure, a rarefaction pulse. Okay, let me cross check the spelling. थोड़ा सा अजीब सा doubt आ रहा है. Is it? It's rarefaction. The rarefaction pulse is a region of deficit pressure, which is below the atmospheric pressure. Okay? Region of deficit pressure below the atmospheric pressure. That's your rarefaction pulse. Okay, ये there क्यों है? There का जरूरत नहीं है. So rather I'll say therefore sound seems to be. Okay, therefore sound seems to be a pressure wave. What do I mean by saying that it's a pressure wave? It's a you have consecutive compression pulses and rarefaction pulses. Right? That's what's making up this pressure wave. There's a region of high pressure, low pressure, high pressure, low pressure. So therefore, sound seems to be a high pressure, low pressure kind of wave propagating in the forward direction. Just like in water, you have when wave, or rather when waves on a string propagates, you have a crest and a trough which keeps moving forward. यहाँ पे you have high pressure, low pressure, a compression and a rarefaction which keeps moving forward. All particles are also performing an SHM about their mean position in the direction of propagation. All particles are performing an SHM in their mean position, about their mean position, okay, about their mean position in the direction of propagation. So if you remember, particle 2 went to its extreme, came back, went to the negative extreme, came back. All of this was parallel to the line along which the sound wave was propagating. So the phase of this phase of the SHM for any particle that propagates forward. Therefore, sound is a displacement wave. Okay, so on that note, you can consider sound to be a displacement wave, because the displacement of a particle or the phase of a particle during its SHM that propagates forward. What do I mean? Like over here, when this guy in the first when this guy had a displacement of plus a, when this guy was at a phase of pi by 2, that plus a displacement, yeah, that pi by 2 phase, वो propagate होते गया आगे, अगला पार्टिकल का चांस आ गया प्लस ए पे जाने का और पाई बाय 2 फेज होने का, फिर अगला पार्टिकल का चांस आ गया प्लस ए पे जाने का पाई बाय 2 फेज जाने का, फिर उसके अगला पार्टिकल का चांस आ गया. So that displacement is propagating forward. Displacement for the first particle or the phase of that particle that is getting propagated with time. वो आगे आगे पुश होते जा रहा है. Pi by 2 phase, subsequent particles down the line are reaching their positive extreme when the wave reaches them. ठीक है? So compression and rarefaction pulses propagate हो रहा है, आगे जा रहा है, और ये phase एक particle का displacement जो है वो भी subsequent particles को मिल रहा है, वो भी आगे जाते जाते propagate हो रहा है along with the wave velocity. So sound is, as we have mentioned earlier, as we have categorized this, sound is therefore a longitudinal wave, you know, because the oscillations are in the direction of propagation, उसको बोलते हैं longitudinal, और अगर perpendicular है तो उसको transverse बोलते हैं. Waves on a string, waves on the surface of water, they were light itself, they are all transverse waves. And sound is a mechanical wave because it involves particles of the medium. So all waves are mechanical waves because they involve particles in the medium, except light. Light does not involve particles in the medium. Light is an oscillating electric and magnetic field. The speed of sound. Okay, so sound is a mechanical wave. Based on all of this, I can also comment that the speed of sound would depend on Pulse modulus, on the pulse modulus for fluids. Okay, and the Young's modulus, and this is eta, coefficient of rigidity. Okay, coefficient, torsional constant, coefficient of rigidity. So for solids, it will depend on Young's modulus and the torsional constant. We'll derive a couple of these formulas a little later, maybe today itself. But why am I mentioning this over here? Because you can see how the wave propagates. It's clearly an indication of the tendency of a medium to resist compression. It's clearly the indication of the tendency of a medium to resist compression, right? So, for instance, this over here, this dislike for being close, that dislike for compression was the driving factor. The dislike for compression was the driving factor. If this medium had no problem with these molecules sitting like this, sound would have not propagated. है ना? जितना desperately वो इसको oppose करेगा, उतना जल्दी ये particle वापस जाएगा, ये particle उधर जाएगा. So how desperately the medium opposes compression, that quickly the wave will propagate. So if you have to, based on that, tell me, answer this. Based on that, answer this. किस medium में sound will propagate the fastest? Solids, liquids, and gases. Arrange them in from fastest to slowest. Right? Think, who does not like compression at all? Most of your answers are right. Who does not like this compression? Who is, for whom this is irritating? So the more rigid a body, the more it will dislike this kind of compression and all produced. Right? So solids are more rigid. Solids hate compression more, as opposed to liquids, as opposed to your last one is gases. Gases, of course, gases to compressible hota hai fairly. Okay? So gases के लिए सबसे कम होगा. So based on that, you'll find कि the speed of sound would depend on bulbs. So coming back, we find the result is sound is thus the fastest in solids, then in liquids, then in gases. The solids may it's most irritated when those molecules come close. The solid may it will quickly try to resolve the matter, and then the wave will propagate faster and faster. It's like a string with higher tension, where velocity is faster, because tension did not like, or tension tries to oppose a crest like that being formed. Tension tries to straighten out the wire. तो ज्यादा टेंशन मतलब उसको ये कम पसंद आएगा, और इसको जल्दी से वापस लौटने की कोशिश में वेव जल्दी प्रोपगेट होगा. Right? So therefore, larger tension causes a greater, causes faster traveling wave on a string. Similarly, more rigidity, more opposition to compression causes faster waves, faster sound waves in solids than in liquids, than in gases. Any doubt in this? Just give me a second, I'll just be back. I'll just be back. sorry. Yeah, moving on now to the next page. We'll try to find a relation between the displacement wave and the pressure wave. Okay. So first and foremost, since the prongs of the tuning fork or any vibrating body for that matter, since they more or less always perform an SHM, okay, any vibrating body, if you even if you tap any object, if you observe the molecules at a molecular level, you normally always find them to perform an SHM. So since the prongs of the tuning fork or any vibrating body for that matter, they normally perform an SHM. Therefore, so do the particles propagating the sound. Okay, the way the original source was vibrating, like when you beat the skin of a drum, the way the skin of the drum is going to vibrate, वैसे ही उसके बगल में जो air molecules है वैसे ही वो भी vibrate करेगा. Strum गिटार उसमें कैसे string कैसा vibrate करता है वैसे ही बगल वाले particles भी sinusoidally vibrate करेंगे. So it's fair to assume that the displacement of the displacement wave that propagates down the string is a sine wave. So this is how we can write the displacement wave equation for sound. Okay, now let me explain a couple of these terms. So first of all, omega will be exactly the same as the source's omega. This rate pe tuning fork, as you saw, the oscillation of the first particle on the first page was the same, was in sync with the tuning fork का prong का oscillation. वो जैसा आगे पीछे गया वो particle भी आगे पीछे गया. So the frequency of the oscillation is going to be the same as that of the source. फिर the displace, अब इसमें what does S mean? What do I mean by S? S naught, of course, is some amplitude. This, of course, we can understand this is like a traveling wave equation. We are comfortable with understanding why is S naught sine omega t minus kx. Right? Why is A sine omega t minus kx? Why is S naught sine omega t minus kx? We can understand that. That would be the equation of a transverse wave where oscillations are perpendicular to the line joining them, perpendicular to the direction of propagation. यहाँ पे S actually means, if by the way I've taken my x-axis along the direction of propagation, S means displacement of the particle whose mean position is x along the positive x-axis. Okay, so this equation is telling me what a particle जिसका mean position x था, अब वो displace होने के कारण फिलहाल और किधर हो सकता है, but I can at least identify each different particle with their mean position. Their mean position is unique for all particles in a line, right? Mean position is unique. वो mean position से थोड़ा आगे पीछे जा रहा होगा, right? But mean position जो है उसका originally वो सबके लिए unique है. So in terms of the mean position of that particle and in terms of the current instant of time, this equation helps me understand how far that particle has been displaced along positive x, along the x-axis itself. In terms of its mean position ka x coordinate and in terms of time, this equation tells me how far that particle has been displaced along the x-axis. Okay, so जैसे अगर just ज़्यादा इसमें dig नहीं करना है, but if my particle was at x equal to 2, like a particle जिसका mean position is x equal to 2 और वो x equal to 2 वगैरह डालने में अगर मुझे वहां से मिलता है कि s is 0.1, मतलब the particle is currently at 2.1, is displaced 0.1 along positive x. था किधर पहले mean position 2 था, s 0.1 उस particle के लिए आ रहा है, मतलब वो अब 2 से और 0.1 x axis के along displace होके फिलहाल 2.1 पे. That 2.1 is the current position. वो इस equation में नहीं डाल रहे, हम उसका mean position equation में डाल रहे. थियरेटिकली तुम्हें वैसे बैठ के कुछ डालना नहीं पड़ेगा, बट how does this अच्छा ये क्या, how does this info about a particular particle tell us about the wave? So this is actually the entire wave equation. Wave is nothing but what all the particles are doing. So zoom out, and if you look at the function of x and t, that's your wave equation. A particular x will tell you what a particular particle is doing. Okay? This entire equation tells us what the entire wave is doing. So as we have seen this term before, omega t minus kx tells us that that disturbance, light in a transverse wave, is going to move along positive x. Same funde, same concepts. Wave velocity is still omega by k. See, I still have that over here. Wave velocity is still omega by k. Different signs still means positive x. Same sign still means negative x. All those concepts are still valid. Only change is, instead of the particle going like that, the particle is going like this. Particle is moving about its mean position along the x-axis itself. Okay, that's the only difference. All right. Now, have a look at this diagram below it. Okay, so let's just take a column of air. Okay, let's just take a column of air through which my sound is propagating. Okay, let's say that particular column of air's area is A. Okay, let's say the column of air's area is A. It's soon going to disappear from the equation. So you need not worry about what A, how wide should the column be. It's going to disappear from the equation. But Philal, let's just focus on a area, cylindrical volume of area A. Let's say that I have one particle jiska x coordinate is x. Okay, or a set of particles jinka x coordinate is x, and another set of particles jinka x coordinate is slightly more than x. यहाँ पे मैंने बड़ा diagram बनाया, but actually this is slightly bigger value of x. So this is x plus dx. Okay, just slightly down the x-axis. These, what I've labeled in red, are the mean positions of those particles. These are the mean positions. Now, based on their x coordinate, we can get the displacement of each particle. So let's say the guy at x coordinate x has been displaced by an amount s. Okay, और अब उसका mean position x के जगह x plus dx लेने के कारण, mean position x के जगह x plus dx लेने के कारण, ये पार्टिकल का डिस्प्लेसमेंट s के जगह s plus ds आएगा. Okay, it's going to be slightly different. It's at a different position, will have a different displacement. ds will exactly come from ds by dx. Get the value of ds, we'll have to find ds by dx. Okay, वहां से we'll come to know कि थोड़ा आगे बढ़ने के कारण x कोऑर्डिनेट हल्का सा चेंज करने के कारण कोई पार्टिकल का मीन पोजीशन से डिस्प्लेसमेंट कितने से चेंज होता है. That's what calculus will tell us. And that's what differentiation means also. x को dx से बढ़ाया तो डिस्प्लेसमेंट ds से बढ़ गया. Right? Now, if you look at what was the original volume between the two particles, so the particles ka original position was as shown by the two red lines, right? The original volume between these two particles is a into this distance. As we can see, this distance is dx, right? This distance is dx. So the original volume between the two particles was area into dx. Okay, the increased volume, the volume has changed. कितने से change हुआ? What is delta v? What is dv in fact? कितने से volume change हुआ? Okay, so volume has changed. First of all, volume has increased when this boundary went ahead. This volume increased when the right boundary went ahead. It increased by this amount. What is that amount? Area into length. So it increased by area into s plus ds. It increased by area into s plus ds, and it decreased by So the volume has increased, but then it has decreased because this boundary has moved in. कितने से decrease हुआ, इतने volume से decrease हुआ, A ऐसे कम हुआ. It's quite clear to see कैसे the length between the two lines has increased by s plus ds and decreased by s. So it has basically increased by ds. The length between the two vertical lines has basically increased by ds. एक लाइन s गया, एक लाइन s plus ds गया, आगे वाला s plus ds गया, जिसके कारण इनके बीच में डिस्टेंस एक्स्ट्रा ds से बढ़ गया. So that extra distance into area gives the increased volume. So increased volume is ADS. It's very simple to work this out. We have all of this. ds by dx निकाल के रखते हैं, है ना? So ds by dx, you have to just differentiate this equation. You will get एक तो partial derivative लेना है, ठीक है? Of course, I mean dou s by dou x. Partial derivative लोगे, you can write ds by dx also if it's obvious what is meant. तो x के रिस्पेक्ट में डिफरेंशिएट करना है, तो माइनस के बाहर आ जाएगा, x का कोएफिशिएंट बाहर आ जाएगा, और बाकी s नॉट साइन का डेरिवेटिव हो जाएगा s नॉट cos. This entire thing will become s नॉट cos omega t minus kx. Okay, s नॉट cos omega t minus kx. Minus k s not cos omega t minus kx. So this is ds by dx. Okay, now we are ready to apply. We are ready to now bring in pressure into the equation. So bulk's modulus is actually what relates a small change in volume to a change in pressure. You might remember bulk's modulus is negative volumetric stress by volumetric strain, right? So वहां से आ जाता है कि volumetric stress मतलब bulk's modulus is minus P by dV by V. And you remember me making an issue of this earlier. P is not technically current pressure, but P represents excess pressure over the atmospheric pressure. It represents excess pressure over the atmospheric pressure. Yeah, it's your gauge pressure. Very nice. That's your gauge pressure. When dV is 0, P is also going to be 0. That doesn't mean pressure is 0 here. It just means when there is no change in volume, your pressure is the normal pressure. कुछ compression वगैरह rarefaction नहीं है, तो it's the normal atmospheric pressure. Compression है, dV positive है, तो compression है, dV negative है, तो P positive होता है, मतलब pressure बढ़ता है. और rarefaction है, dV negative है, rarefaction में dV positive होता है, rarefaction में dV positive होता है, volume बढ़ता है, और pressure negative होता है. Bigger volume, lesser pressure, lesser volume, bigger pressure. We also do that. Okay, I'll continue the derivation on the next page. Let me know if you've copied this. Let me know if anyone wants me to wait. If I have to wait, jaldi wait for you. Okay. Let me know when you're done. Done? Okay. Now, so वही equation से आता है, if you write pressure, then pressure becomes minus B dV by V. dV, the small increment in volume we were considering in that for that small element of size dx, the small increment in volume was area ds, whereas the volume of that element itself was area dx. The displacement के कारण, अलग displacements के कारण volume a ds से बढ़ गया था. So now when I divide dv by v, ads by adx, एक कट जाता है, and pressure comes out to be this minus b into ds by dx. That's how actually pressure, long story short, that's how pressure relates with um, displacement. Okay, if you ever need to use this equation, if you're ever given the displacement equation and you want to find the pressure equation, and you don't think you have the patience to make this entire derivation that I did, then you can use this result. Rare है कि कोई exactly ये पूछता है, but yes, if you have to convert from pressure to displacement, if somebody asks, you can always use this equation. P is minus B ds by dx. It comes from dv by v, and dv by v is ds by dx. Okay. Now, performing that, you remember we found ds by dx in the previous page. Ds by dx was minus k s naught cos omega t minus kx. एक minus sign था, और उसके सामने जब तुम माइनस बी मल्टीप्लाई कर लोगे तो माइनस साइन हटके इधर एक बी आ जाएगा. सो देयरफॉर our pressure equation becomes b ks naught cos omega t minus kx. Okay, now this entire thing over here becomes our pressure amplitude. Okay, so p naught is our pressure amplitude. So what we see over here is now a relation between the pressure amplitude and the displacement amplitude. This is an important relation. Pressure amplitude and displacement amplitude के बीच में the relation is pressure amplitude is bk displacement amplitude. Okay, so that is one important point to remember. The other point you can remember is that there is a difference, there is a phase difference of pi by 2 between pressure and displacement. In the pressure and the displacement, there's a phase difference of pi by 2 between them. उतना याद करो. कौन exactly positive cos, negative cos, वो सब situation पे depend करेगा. This is the exact equation. Will it be positive cos, negative cos will depend on how you write s. Yeah? You know how that works. Exact value will depend on whether you write s as omega t minus kx or kx minus omega t. Okay, but the fact of the matter is, whatever be that thing, the phase difference will be pi by 2. एक आगे होगा, एक पीछे होगा, एक sin होगा, एक cos होगा, but the phase difference will definitely be pi by 2. So remember that. Pressure extreme पे displacement mean position होता है. Displacement के extreme पे pressure mean position होता है. Yeah, remember that. Cool. Then you have this other important point where we see that human ears and electronic detectors in general, how the world perceives sound, in general, how sound interferes with other sounds. Okay, the way that is done is via pressure waves and not displacement waves. Not exactly displacement waves. The way sound is actually experienced when it's coming from multiple sources, when they interfere, is actually experienced as a pressure wave, not as oscillating particles. Because placing a detector, imagine this, try placing a detector mentally, okay, exactly between two coherent speakers. So coherent means they are in sync. In sync means they have the same frequency and they also have the same phase. So if you place a detector exactly between two coherent speakers, जिनसे same phase, same frequency के साथ displacement wave same time पे निकल रहा है, then this will imply कि by symmetry जो point exact बीच में है वहां पे तो displacement forever zero होना चाहिए एकदम symmetry से, क्योंकि जो पहले स्पीकर के कारण डिस्प्लेसमेंट होना चाहिए राइट की तरफ, वो सेकंड स्पीकर के कारण डिस्प्लेसमेंट होना चाहिए लेफ्ट की तरफ, राइट. Okay, so this point का displacement will always be zero, but by symmetry, but you will still hear sound, है ना. ऐसा नहीं कि तुम स्पीकर, दो स्पीकर के एग्जैक्ट बीच में सुनोगे, खड़े हो जाओगे तो you will hear zero sound. or you'll hear almost zero sound. ऐसा कभी होगा ही नहीं. Ulta, you will hear a loud sound as good as the addition of the sound coming from both speakers, right? So what is really happening if you place a detector there? Okay, although the displacement at the middle of those two speakers is zero, okay, although the displacement at the detector is zero, yet compression and rarefaction pulses are still present, and thus sound is detected. You still have compression and rarefaction pulses. Okay, you still have the neighboring particles coming close to this guy at some point of time, thereby a compression, and the neighboring particles going far away from that guy at a point of time, thereby a rarefaction. You still have compressions and rarefactions, and sound will be detected in that manner. So for that note, sound is best understood and represented as a pressure wave. Okay, we'll more or less focus on sound as a pressure wave. When it comes to hearing sound, when it comes to how sound interferes, how sound is superposed, okay, you want to treat it as a pressure wave. Okay, because displacement से what we hear का correlation नहीं है. Okay? Displacement zero है, फिर भी वहाँ पे compression rarefaction के कारण sound will be detected. All right. So let's try out a question on this one formula we have seen so far. Okay. So let's say I'm just reading one of the doubts. Can this be considered as a result of fact? Okay, I'll wait. Yeah. Can this be considered as a result of the fact that the phase difference between displacement and pressure waves is pi by 2? I don't think it has to do with, does it have to do with that? In a way, yes. I mean, you are having, but does it have to do with that? I don't think, sorry, I don't think it has to do with that. It has to do with um, just the way we detect sound. It's like if this guy is producing a compression over here, and this guy is producing a compression over here, their effect will just be a double compression produced over there, a greater compression produced over there. Right? That's what their combined effect will look like. But displacement is more directional. यहाँ पे if this guy is producing uh, a leftward extreme displacement, and that guy is producing a right extreme displacement, both are trying to send a displacement along the forward direction. But their combined effect doesn't get added up. The combined effect just cancels out. Right? And you will get more funny, you'll get funnier answers when the speakers are inclined at some angle. So vector addition of displacement से actually कुछ फर्क पड़ता नहीं है, and that's not even how that's not even how sound in general is detected. Sound in general is detected not by the motion of one single particle present at that point. It's detected by that kind of difference in pressure. Maybe the difference in pressure between the outer surface of a eardrum and the inner surface of a eardrum, which I don't know biology, but I'm guessing that maybe maintained at atmospheric pressure. So eardrum के बाहर जो ऊपर नीचे disturbances हैं in pressure, compression में ज़्यादा, rarefaction में कम, compression में ज़्यादा, rarefaction में कम. So accordingly, I feel the compression will cause the eardrum to move in, the rarefaction will cause the eardrum to move out, and that will thereby, them coming at a fast rate will cause the eardrum to vibrate, and to vibrate at the same frequency at which those with the same frequency of the incoming sound wave. And then our mind, in a way, I guess, processes that and enables us to hear the sound of that particular frequency. Okay. And I'm sure detectors also work in a similar manner. So it's um, pressure that we really detect, not the exact direction of motion of our particle. But because anyways, one particle is not going to make a eardrum move. It's a whole combination of effects. It's the entire pressure near the eardrum which will make the eardrum move. Okay, done writing. Whoever was writing this? Okay, so the maximum and minimum pressure detected maximum and minimum pressure detected as the sound wave propagates as the sound wave propagates are 1.4 Pascal and 1.4 Pascal and 1.0 Pascal. Okay. So the maximum and minimum pressure detected as the sound wave propagates are 1.4 Pascal and 1.0 Pascal. Um, if bulks, if if B is, if the pulse modulus is the pulse modulus is um, 1.5 into 10 raised to 3 Pascal. I'll add that into 10 raised to 3 Pascal. 1.5 into 10 raised to 3 Pascal. And the wavelength is 65 centimeters. Wavelength is 65 centimeters. And a, a particle had mean or has mean position has its mean position at x equal to 3 millimeters, then find, this is a question, yes, this is a question. Then find the range, find the region over which it oscillates. Okay, this is your question. This make this bigger. Pulse modulus is 1.5 into 10 raised to 3 Pascal. Okay, so the maximum and minimum pressure detected as a sound wave property is a 1.4 and 1.0. The pulse modulus is 1.5 into 10 raised to 3 Pascal. Wavelength is 65 centimeters, and a particle has its mean position at x equal to 3 millimeters, and find the region over which matlab the particle oscillates. Okay, these are anyways thing made up values. Pulse modulus इतना बड़ा नहीं होता है, but just calculated for what the values are. Yes, sir. क्या आंसर आ रहा है? Come on. You have to use P naught as BKS naught. P naught is BKS naught. No? 2.92 आ रहा है क्या? 2.92 से 3.08. Slight mistake. You're close. I'm getting 2.96 to 3.04. check what you've taken P naught as. Good, nice Nisha. ठीक है, कैसे करना है? Do you guys need more time? P naught 1.4 1.0 के बीच में oscillate कर रहा है. What is the pressure, amplitude? It just probably means कि see the average is clearly not 1.0. So in this case, of course, it means कि P-ATM ज़्यादा है. In fact, P-ATM on an average 1.2 है. You're in some other new place where the ये ATM भी नहीं. This is some P average degree. So average pressure in general is 1.2, okay, Pascal. Okay, let's see what the answer is. क्या है your answer? But 3 से तो मतलब answer तो 3 से पीछे जाना चाहिए ना? It should be around 3 millimeters. It can't be mean 3 millimeters is the mean position. It should be at the exact middle of your answer. Okay, so first we'll find the pressure amplitude. Okay, so we know that 1.4 pascals is the max amplitude. We also know 1.0 pascals is the minimum amplitude. That is the minimum pressure. 1.4 is the max pressure, 1.0 is the minimum pressure. That makes the amplitude. See, the distance between the two extremes is always twice the amplitude. Right? So that makes our amplitude 0.4. Sorry, that makes our amplitude 0.2. 0.4 is 2 P naught. So our amplitude is 0.2. Okay, and solve them simultaneously, or you can just visualize है ना, mean position उसके बीच में होना चाहिए, mean pressure उसके बीच में होना चाहिए, उससे 0.2 पास्कल ऊपर और 0.2 पास्कल नीचे, you have the two extremes. So therefore your pressure amplitude is 0.2 pascal. Pressure amplitude is 0.2 pascal. फिर the next thing you'll do is you'll use you want S naught, right? You want to know how the particle oscillates. So S naught is P naught is BK S naught, so S naught is P naught by BK. We don't have K, but we know lambda, so we can write this as P naught lambda by 2 pi B. P naught lambda by 2 pi B. Okay, P naught lambda by 2 pi B. All right. और यहाँ से substitute everything, you should get your answer. So P naught 0.2. Sorry, P naught is 0.2. Lambda is 65 centimeters. So 0.6 into pi in SI units. B is 1.5 into 10 power 3. Normally इतना बड़ा नहीं होता है B. B is anyways 1.5 into 10 power 3. And दूसरा क्या है? 2 pi, right? So into 2 into pi. यहाँ से you'll get your answer. Pi कटेगा. 2 into 1.5 is 3. That makes this 3, and that makes this 0.2. And of course, you can do that calculation. जिसके कारण ये आ जाएगा 0.04 into 10 to the power minus 3. 0.04 into 10 to the power minus 3. And 10 to the power minus 3 को हम millimeters में लिख सकते हैं. 0.04 millimeters. Okay. And now the range in which the particle oscillates will be from x, basic x coordinate minus s naught to x coordinate plus s naught, है ना. इस ये दो extreme के बीच में particle oscillate करेगा. So it will oscillate between 3 minus 0.04, which is 2.96, to 3.04. Got it? So that's how your pressure amplitude and your displacement amplitude are related. If I give you pressure amplitude, you can use BKS naught to find your displacement amplitude. Okay? I hope you guys understood this. Anyone has a doubt in this? समझा? Pressure दिया है, B दिया है, K दिया है, वहाँ से S naught आ जाएगा. S naught means particle mean position के आगे पीछे उतना amplitude से oscillate कर रहा है. Mean position के आगे पीछे उतने amplitude से oscillate कर रहा है. और P average मतलब यार यहाँ पे if I tell you that a particle का pressure is going from 1.0 to 1.4, so this is the max value, this is the minimum value. Where do you think the average pressure lies? It should have an average pressure, right? It should have an average pressure, right? So that average pressure has to be between 1.4 and 1.0 and exactly 1.2, right? और 1.2 पास्कल से फिर मीन पोजीशन से 1.4 तक जाने में कितना एम्पलीट्यूड आएगा? 0.2 ही तो आएगा. It's like SHM में if I would have told you a particle is oscillating between 7 and 10, what would be its amplitude? If it's oscillating between x equal to 7 and x equal to 10, max x is 10, minimum x is 7. Wouldn't you say 10 minus 7, 3 का आधा is your amplitude? Max और min के बीच में distance 2a होता है. 8.5 mean position है, 1.5 amplitude है ना. तो वैसे ही सीन है यहाँ पे. और shouldn't lambda be, क्या बोल रहे हो? Shouldn't lambda be 6.5? Lambda 65 centimeters दिया है. I've written everything in meters. So in meters, 60 becomes 0.6. सब कुछ meters में होता है. Alright. Okay. Now, let's see how to derive a formula for the speed of sound. The speed of sound. Okay. So again, we're going to work predominantly in air itself. So like before, let's take the nice control volume that we had. Okay. And let's say कि यहाँ पे we have a cross section area. यहाँ पे we have another cross section area. Let's again take this x coordinate as x and that x coordinate as x plus dx. Okay. Let's take the pressure over here as P. We now know how pressure changes with x. let's take the pressure just outside that point as P plus TP. Okay. And let's keep our cross-sectional area as A. Now, with all of this, our let's just even write our displacement and our pressure equations and keep. So let me just fit it over here. My displacement is S naught sine omega t minus kx and likewise my pressure equation is P naught cos omega t minus kx. We all know that P naught is bk S naught. Sorry. So this is the same. Okay. So S naught pata hai, P naught pata hai. P naught is bk S naught. Now, the force we're going to try and write, we're going to apply Newton's second law on this element between x and dx. That is interestingly enough going to help us get our velocities. Okay, so let's apply Newton's second law. So the force that we apply, okay, force that we apply in the forward direction is going to be PA. Yeah, x-axis is in the right direction. Force along the x-axis is pressure into A. Okay, pressure into A. ये यहाँ से उसको force मिल रहा है pressure into A का, और वहां से उसको opposite direction में P plus dP into A का force मिल रहा है. तो आगे की तरफ PA minus पीछे की तरफ P plus dP into A. Yes, F on our element. Okay, this element, this is our element. This is our system. जिसपे हम फोर्स लगाएंगे. तो F is PA minus P plus dP into A. ठीक है, ये अपना फोर्स है. तो फोर्स है माइनस dP A. फोर्स है माइनस dP A. Okay. Then उसके बाद है mass. Alright, so mass is density into area into dx. Mass is density into volume. So rho A dx हो जाएगा अपना mass. Okay, so we have force now. Force by mass निकाल के रख सकते हैं. Okay, the force by mass is going to be minus dP by dA. Sorry, minus dPA by rho A dx. And then we can cancel out A and we'll get minus 1 by rho dP by dx. Minus 1 upon rho dP by dx. With dP by dx, an equation is right in front of you. Let's differentiate that. Okay, so dP by dx is going to give me minus, that's going to give me pressure gradient, you're right. ये बट वैल्यू क्या आ जाएगा इसका, दैट्स राइट, प्रेशर ग्रेडियंट होगा और वैल्यू आ जाएगा, पहले तो वो चेन रूल से माइनस के में बाहर निकाल रहा हूँ, ठीक है, माइनस के बाहर निकाल दिया, पी नॉट भी बाहर निकाल दिया और कॉस का डेरिवेटिव साइन, इनफैक्ट माइनस साइन हो गया ये, लॉट ऑफ माइनस साइंस इन दिस टर्म। सो एक तो माइनस dp by dx by रो, ओके, तो वो एक माइनस साइन है, फिर चेन रूल में माइनस साइन बाहर आ गया और कॉस का एक माइनस साइन हो गया, तो naturally then you can simplify this. Let's also write p naught as bk s naught. So writing p naught as bk s naught makes this thing writing p naught as bk s naught makes this minus bk square s naught sine omega t minus kx by rho. So this is what force by mass is coming out to be. And we know force by mass is going to be acceleration. But let's find acceleration another way. Okay, let's find acceleration another way. So to find acceleration, what we need is displacement का derivative with respect to time. Okay. So acceleration के लिए displacement को differentiate करेंगे with respect to time. So acceleration is double derivative of displacement. Remember, it's not the double derivative of x. X is simply our mean position. The way that particle at that mean position moves depends on s. So s का double derivative, can we do it directly? I think कर सकते हैं ना, उतना आता है calculus. Directly करेंगे ये, actually इसको दो बार differentiate करोगे तो minus के दो बार बाहर आ जाएगा. One I can write that minus k दो बार बाहर आ जाएगा, and then s naught रह जाएगा, and sine itself when you differentiate twice, you know कि वो cos होके minus sine हो जाता है, minus sine omega t minus kx, ये है sine वाले function का double derivative. Just give me a minute. Omega t minus kx. Okay. So that's our acceleration. Okay. So k square s naught. Of course, I'm not going to rewrite this. K square s naught minus sine omega t minus kx. So from this, I'm so sorry. K square नहीं, omega square है ना? ये इस बार time का derivative है. Omega square s naught. Omega square s naught. Omega square. Time का respect में derivative चाहिए. ठीक है? Sine का तो derivative ये हो जाएगा, double derivative. But time का जब दो बार तुम differentiate करोगे, मतलब दोनों बार chain rule के कारण omega omega मान के ये ऐसा. All right. Then of course the next step we know acceleration is force by mass. What does that give us? What do we get when we equate these two? So there is when we equate these two, you have minus b k square by rho s naught sine omega t minus kx. I can maybe save a little space by just writing sine phase is equal to omega square s naught again sine phase, right? Same thing, sine phase. So as you can see, sine phase was exactly the exact same term. That will cancel out. S naught will also cancel out. Okay, and we have by the way, I had a minus sign, that will also cancel out. Just the minus sign, let me just squeeze that in. Minus sign will also cancel out. Okay, this minus n is there. That will also cancel out. Finally, what we'll get as all of this cancels out, S naught cut here, we'll get k square by omega square as, in fact, I want omega square by k square. So I'll get B by rho is omega square by k square. And we know omega by k is velocity. So B by rho is velocity ka square, which gives me velocity of sound as root B by root B by rho. And this is the velocity of sound in air. Okay, so this is an important formula. This is in fact the velocity of sound in any fluid. Speed of sound in fluids. So you have a bunch of derivations at the beginning of this chapter. That's just some stuff we need to go through. Any doubt in this? Kasya B is root B by rho. I'll just add over here, maybe in the last line. So you understood this, just adding to this. For 1D solids, we need not do the derivation. You can just remember the results. For one-dimensional solids, the process is very similar. So for 1D solids, 1D matlab like a rod. Okay? When sound propagates in a one-dimensional manner through a rod. Okay? So 1D solids, like for instance, rods, stuff like that. In them, you'll find key P naught can be replaced with any guesses? You replace P naught with actually Young's modulus. Okay, so you replace with the Young's modulus K S naught, and velocity accordingly can also be replaced with velocity, maybe P can be replaced with Young's modulus. Okay, but it's this way only for 1D transmission. This is how sound propagates in a rod with this velocity. Okay, as I said, it will depend on y. But rho is linear mass density. Rho is mass by volume. I'll make a note of that as well. Rho is linear mass density. However, in your if you for 2D and 3D bodies, it's a complex function of your Young's modulus and your eta. So you don't need to know this. For 2D and 3D solids, velocity of sound, yeah, that's out of your scope. That's not in your slides. 2D and 3D solids, velocity of sound is a complex function of Young's modulus and eta. Okay, of Young's modulus. Why is Young's modulus? Okay, and eta is your torsional constant. Okay, so this you need not know. 2D and 3D bodies ka formula is out of your syllabus, okay, out of scope. But वैसे तो ज़्यादा solids का इतना ज़्यादा heavy नहीं, but nonetheless you can remember for a 1D solid the substitution is very simple. For 1D solid you just have to replace Bull's modulus with the Young's modulus. 1D solid के लिए just replace Bull's modulus with Young's modulus in both the formulas. The derivation will be very similar. This, in fact, this was more like a 1D situation. Area was fixed. Area was fixed in both the derivations we just did, right? So, वैसे ही result 1D solid के लिए भी आएगा. Rho is linear mass density. Rho is linear mass density. Mass number. All right, maybe we can pause away. Any doubts so far? Please finish your waves. Just finish attempting it by tomorrow. Trust me, it's all just on the definition of, what, just on the understanding of what your first harmonic is, what your second harmonic is. They're all very simple. Almost all the questions are on both ends being fixed. Try it out. We'll just see if the HCV solution playlist helps. Maybe you may just need to see one or two in the beginning, then you'll get the flow. But nonetheless, let's discuss our doubts tomorrow. Then we can do maybe something extra, और थोड़ा practice करना है standing waves को कर सकते. Cool. By one is saying, why can't we do the same method for why can't we apply the same method for 2D and 3D solids? 2D, 3D solids, do you understand how complex it is? Sound is not propagating in one direction now. It's propagating in 3 directions. And the way it propagates in 3 directions, it not only causes a kind of, it not only causes compressions and extensions, it also causes changes in shape. And the way a solid responds to a change in shape involves the use of eta. Therefore, it's not going to be similar. For a liquid, it's very straightforward. Liquid में सीधी सी बात है, liquid को change in shape से फर्क नहीं पड़ता है, इसलिए eta कभी आता नहीं है. वो उधर सिर्फ liquid doesn't have an eta. Liquids and gases don't have eta. They don't oppose the change in shape. So उसमें सिर्फ compressibility का factor आ जाता है. Okay, cool. We'll stop over here. See you tomorrow. Please try to finish attempting. I think it's just 20 questions. Do them by tomorrow. Bye. Obviously, these are in the next folder. Sound waves नाम के folder में you find all these notes and the recording. Yeah. Can bring these 2 folders out. Bye.